A 3DG position is represented as a set of XYZ coordinates at a given instant in time. And there are a number of ways that we describe a GPS position, including position status, which is represented as 2D, 3D, or differential. 2D refers to two-dimensional GPS, and it's a horizontal position that is calculated by at least 3 satellites. A 3D position, it describes a vertical and horizontal position that's calculated utilizing 4 satellites. A differential position is something that we'll talk about in just a minute that describes a way to reduce the amount of error in your position. Height above ellipsoid is how we calculate our vertical position. The height above ellipsoid is the altitude expressed as height above the datum, or that's the model sphere of the Earth. And then we use the antenna height, which is the height of the antenna, and we subtract that from the GPS altitude to calculate the height above ellipsoid. Position averaging is where we average the number of positions into a single point. So I might, for example, stand in one location and collect 60 positions over 60 seconds, and then I average those positions into a single point to try to average out any error in the positions. Now, when we're collecting positions in a single location, that's referred to as a static position, but if we are moving, it's referred to as a streaming position. Now, with all the moving parts associated with calculating your position utilizing GPS, there are a lot of places that error can creep into your position. Now, we represent error in GPS as the position error, and that's a circle in which our position is located. And in this example right here, the position error is plus or minus 100 feet, which means it's not very accurate. But if it's plus or minus 10 feet, it means I know my position within 10 feet of this location. Now, there are ways that we describe that error, and we can utilize our understanding of the error to try to mitigate it. Signal to noise ratio describes error that creeps in from things like thunderstorms or nearby radio towers that are disrupting the signal that's coming from the satellite. And so the more noise that you have, the more it can disturb the signal, which can affect your calculation of your position. And so you really want to lower your SNR ratio so that you don't have a distorted signal. The elevation mask angle is a way for us to reduce distortion created from satellites that are low on the horizon. If you pick up a satellite that's low on the horizon, it means the signal has to pass through a lot more of the atmosphere where it can bounce around and can affect the time it takes to get to the GPS receiver. And so a lot of times we'll set an elevation mask angle, for example, of 15 or 20 so that we won't accept any satellite signals that are below the elevation mask angle. Differential correction is a way to mitigate the error, and it's something we'll talk about in just a second. And when you use differential correction to calculate your position, as your position ages and that information associated with the differential signal ages as well, then your position tends to degrade. So the age of the time from which you got the differential correction is something that we consider when we're calculating our GPS error. Now we measure the overall error utilizing the DOP, or the dilution of precision. And the composite measurement is the PDOP, in which we combine all the different DOPs into a single measure that tells us something about the accuracy of our position. There are other DOPs as well as the positional dilution of precision, and that includes horizontal DOP, vertical DOP, timing DOP, and geometry DOP. But we typically just keep an eye on the PDOP, and we want to make sure that it's under 5, for example, for most of our GPS activity. But if we're doing, for example, survey grade work, it needs to be really under 2 to get a really tight position. So how do we reduce all the error that creeps into our position? One way is to use differential GPS, in which a correction message is transmitted to the GPS receiver to account for error. How it works is a stationary GPS receiver is placed on a surveyed position, and then the differential is the difference between the surveyed position and the GPS position for that same location at a point in time. The correction message is then transmitted via a geostationary satellite, a ground-based antenna, or maybe just the internet. If the differential correction is applied in real time, it's referred to as real-time differential correction, in which the GPS receiver gets the signal from the satellite and also gets the signal from the differential correction and corrects the position. Sometimes, though, land surveyors, for example, want to have more control over the process. So they'll collect the GPS position, they'll collect the differential correction signal, And then back in the office, they'll use the differential correction to improve the GPS position on a computer. That's referred to as post-processing. If you look at the image in the lower right-hand corner, you can see how this works. The lighthouse is the known location in which there is a stationary GPS receiver, and it's calculating the error in the position of the GPS signal, and then it is communicating that out via the radio tower out to a boat that is then also collecting the GPS signal and correcting it using the differential correction signal. When the differential correction is conveyed via geostationary satellite, it's referred to as a satellite-based augmentation system, or SBAS. In the United States, we utilize WAAS, or Wide Area Augmentation System. It is a system operated by the FAA in which there are 3 geostationary satellites, one directly overhead, one over the East Coast, and one over the West Coast. But if you're in Europe or in India or in China, you're going to utilize a different SBAS system to correct your GPS position.